Can you go to the other room, please? Ramya.
Sorry?
It was just somebody who forgot to turn off their microphone.
Ah, okay, no problems. Oops. I realize I forgot to put a link in here.
Hello, everyone. Welcome to our fourth lecture on radio astronomy. Our speaker today is again Dr. Jeff Hodson. So I guess we may begin. So Jeff, please.
Yeah, thanks again. Hello, everyone. I hope you had a good week. Reading from Korea, hopefully not too shiny behind me. The sun's bright. The cherry blossoms are here, which is nice. Yeah, so last week, hopefully you might remember I got you to download some data from the Mojave website, and then got a little bit of a play around with it. So we'll continue on from there. So what I think I'm going to do is I will download some data for now, again, I suppose. And then I will make an image out of it, and you guys can follow along. But then not worry too much about it, because then I'll go back to these slides explain a bit more about what I was actually doing, and then hopefully everyone can play around with themselves, and then we can finish off with well, you can see the link there. It's for the Event Horizon Telescope, so we can try and make our own black hole image. So let's dive into it. So you might remember last week. So the link I have there, we have this page, which is the Mojave page. If you're probably for now, the easiest option, unless you have run ahead a little bit, is just to follow what I'm doing. So the source 1227 plus 255. So that's somewhere down here is organized by right ascension. So here ON246, 1227 plus 255. So you can try find that on the website. I'll give it a few seconds for people to catch up, so I don't move too quickly. If I'm moving too quickly, feel free just to speak up and say, please slow down. That's fine. I know people always say, please say that. No one ever does, but I would appreciate it if you do, or put something in the chat, which I have up here. But yeah. So has everyone managed to get to at least to the website? Cool. And so at least some people have. And then once you're there, just click on the link. Like so. And you can see this kind of beautiful looking AGN jet. So just as a reminder, so what we're looking at here actually is, so I can zoom in a bit just for now. So a little bit of a busy image here, but this is an animated GIF of the structure of an AGN, an active galactic nuclei jet. So basically, what we think we're looking at here is something very, very close to the central supermassive black hole in probably massive elliptical galaxies, although that's a big topic in and of itself. The colors here are actually related to polarization. We haven't touched on this today, so you don't need to worry about them. But the important thing to look at is the contours here. This is the structure of the jet. So basically, up here where my mouse pointer is what we call the core of the jet. The physical nature of that is a little bit controversial, but at these wavelengths, it's probably a you can sort of think of it as a okay, yeah, sorry. You can think of it as being a cloud of synchrotron emission somehow. So we call it synchrotron self-Compton, but synchrotron self-absorbed emission, I should say. So I won't go into the details of the physics here, which is of course very interesting, but basically what you need to know is that this is probably within maybe some light years of the central supermassive black hole. And of course, a light year is a long way, but in the context of a galaxy, which is sometimes millions, if not more, of light years across, then this is really, really close. It's like within the central 0.01% of a galaxy, or even less than that. And beyond, and then these jets, they basically spill out and go clear across the galaxy quite often. So that's basically what we're looking at here, in a roughly physical sense. Okay. Okay, so what we want to do is we want to go down to this table at the bottom. So we did this last week as well, but let's just take the top one here, and it said the visibility data, and it has a UVF column here. So you can just right mouse click it and take copy link address. So we did this last week, but it can't hurt to do this again if you're unfamiliar with these sorts of processes. So is everyone caught up to that? So just you right mouse click on the UVF link and copy link address. Done. Good. Okay. So oops. Okay, so let's dot here. We go. Cool. Let's go make directory, something like Mojave imaging, something like that. And then we can go CD Mojave imaging. So all I did here for people who are not familiar with Linux is that I created a directory, mkdir, make directory. In this case, I just named it Mojave imaging, and then I CD'd into the Mojave imaging directory like that. And once you're there, you just type wget, then paste in the link that you copied from the website and press enter. And then you should download the website. Not the website, the should download the data file. I'll give people a little bit of time just to catch up. Okay. So I hope everyone's caught up. Is there anyone who, I'm just looking at the chat now, is there anyone who needs a bit more time? If you don't feel shy, just to say, okay, you still need more time, no problems. Which part are you stuck at? So just remember, I'll do the procedure again just for, okay. So are you under Linux, Mac, or Windows subsystem for Linux? You have to Linux. Okay, good. Yeah, it's always better to be on Linux. It's funnily enough, I think it's legitimately the best operating system these days. It's not something I expected to say even 5 years ago. Yeah, so are you on the website? Okay, and then have you right-clicked and gone on the UVF data and press copy link address? Okay, yeah, let's do it again. Cool. And then once you've done that, we go to the terminal where you have a directory. Hang on, I'll move the move to workspace down. Cool. And then in the terminal, you just type get, and then you paste the link and press enter. Okay, good, good. Great. So hopefully everyone's caught up to us now. Yeah, that's totally fine. You know, these things can be a little bit tricky if you're not familiar. Once you've done it 100,000 times, of course, then you sort of get it used to it. But that's fine. Good. So next step is, you might remember this from last time, is type diffmap like so, and then you do type observe. You can do tab completion if you like, and then what's the file name? 1227. So yeah, just when you're using diffmap, you can type tab, and it will automatically complete the line for you if it knows if there's no other options, basically. You press enter, and it should come up with something like this. And just to confirm, you can still see my screen here. Great. Perfect. Good. Good. Now, and have you managed to read the data into diffmap successfully? So, yeah, sure, I can do that, no problems. Is that better? Okay. Yeah, is that easy enough to read now? Cool, perfect. Good. I'll exit out again, just to make it a bit easier for you. So ls, so there's my file. So you just type diffmap like so, and then observe like this. I recommend just typing tab. So OBS tab. So observe and then tab. That makes it full like this. You can type it out if you like, but OBS observe like this. And then because the file name is 1227, just type 1, 2, tab. No problems. How do you say no worries in I forgot about how to say that in Romanian. But something like that. Anyway. Which file did you download? It doesn't really matter too much which file you got. So did you manage to download a file at all? ls. ls is what you type. Yeah. So yeah, if you're not familiar with Linux, I'll quit out again. So just give you a few basics. So ls is the same as dir from Windows. Need of Spectra. I'm not sure what you mean by that. I mean, quasar spectra. I mean, that's a big topic. I mean, you need to define what kind of frequencies you're looking at. So, yeah, presumably you mean optical spectra, probably not VLBI spectra. But yeah, that's not what we're doing here. It's a bit different. So, but for now, are you up to speed with, are you managed to load your data into diffmap? You see, this is the file here that I'm loading. I just type diffmap to start diffmap, and then put everything in here. Anyone need a bit more time? Okay, I'll take that as success, hopefully. Yeah, if you need some more time, just let me know. Otherwise, I'll move on. All right, so I'm going to assume that everyone's doing fine. So the next step is that we just need to select a polarization. You don't really need to worry too much about this at this stage, but let's just select I. That means you're selecting Stokes I. We don't need to worry about that too much at this stage. Then we need to set a map size. In this case, will be 1024 pixels of 0.1 milliarc seconds, like this. Okay, have you successfully managed to do that? Select I polarization and set your map size. No feedback here, so I assume everyone's maybe some people are stuck a little bit. I don't think it'd be anything specifically different with Red Hat. This should work. What's going wrong? Okay, so that's an installation problem. Okay. Yeah. So yeah, that was that was last week. I don't know if I can troubleshoot diffmap installation. Probably it means that something is wrong in you just haven't updated your bash RC file. Did you what was I going to say? Did you manage to install it successfully? Did it work following the recipe? Okay, so maybe I can have a little bit of a hack for you. I don't know if this will work, but if I think what's happening, this might work. So I'll just quickly do this. Do you have the directory where your diffmap was installed? Okay, good. Let me go to where mine is. Here. I think I had to put it somewhere different. Yeah, so if you change to your where your diff map is installed, yep. So if you go to that directory, try running diff map from there, and tell me if it works. Don't know why I named my directory diffmap auto setup testing, but yeah. So are you in that directory? And if you type diffmap here, so what actually happens if you type diffmap from the directory? So you can see when I type ls, I have diffmap here. Try doing /diffmap, see if that works. So instead of typing diffmap, I'll try /diffmap like this. See if that works. Okay, so that works. Good. All right, so then for you, just it's a little bit messy to do it like this, but download the data from the website into this directory, and then run diffmap with /diffmap. Cool. Good. Problem solved. Hopefully. Great. Great. So, and let's head back over to here. So has everybody else managed to catch up and be in diffmap with their map size set like this and polarization selected? So you don't need to worry too much at this stage, because what I'm going to do now, I'm just going to image the source and then go back and explain what I did, and then we can try afterwards ourselves. So next trick, what I'm going to do, I'm just going to do the imaging for us. So when you want to bring up the graphical interface, it'll pop up, say graphics device, just type /xw like this, and it'll come up. So you might remember the basic stuff from last week. So to zoom, you just press Z, a little blue box comes up like this, and it comes in and it says Z. If you want to save the zoom, you press K. If you press H in the, if you press H, it shows all the different options here that you can use. Oops. All right. Anyway, for now, I'm just going to do my going like this. Oops. So you can see here, it looks quite ugly. You can see there the broad idea of what's going on, but it's quite ugly. Lots of noise everywhere. It's not a very nice signal. But I can clean it a bit more, as we say. Something like this. So cleaning is what we call the deconvolution. But there, right here. And now you can see that the source is now looking a lot nicer. Of course, this is good data. I can even turn the sensitivity down. So do a bit more cleaning, like so. Starting to look a bit neater. Not perfect, but this is 0.1% contour level. So this is quite a deep image, and you can see, oops, that we're starting to recover the structure of the jet. So it looks something like this. Okay, so what did I just do there? It looks like a little bit like magic, and you're not wrong. So let's go back to the slides then. So what I did there is actually what we call deconvolution. And let's talk a little bit more about that. So this is the Mojave from last week. We talked about doing all these sorts of things. So the different basics. So here, this is actually where the Stokes I comes from. It's from the Stokes parameters, which is about all the polarizations. If you know a bit about optical polarization, you'll know what that means. But your total intensity basically is your Stokes I. And we looked at this last week. So this is UV plot, this is the UV coverage. So you remember the distance between the furthest points here sets the resolution of your observations. So in fact, here, this is what we call the beam. This is the resolution of the VLBI array. So you can see here it says it the beamful with half maximum. So the beam of the instrument is 0.8 times 0.453 milliarc seconds. And remember, we calculated this last week. So this 0.453 milliarc seconds corresponds, at least roughly, to the distance between the longest, the most separated radio dishes, and that's and then divided by the wavelength, which is 2 centimeters in this case. So you hopefully remember that. Cool. So what are we actually doing here? Okay, cool. So what we do here is Fourier transforms. So I touched on this last week. So remember I said that when we're creating a radio image, we are in effect taking lots and lots of 1D slices across the source and then try to reconstruct the image from that. And that's the idea. Hopefully you remember that from last week. And so on the left here, you can see these are the Fourier transforms actually of 1D slices across the source. So remember, you can think of the Fourier transform as being a way of decomposing something complicated into lots of simple things. And in a way, you can think of interferometry or VLBI imaging as basically taking lots of these simple things and trying to reconstruct the complicated thing that it was decomposed from. You can sort of see here, so this is exactly it. So on the bottom left here, we have, this is actually the UV plane, and this is the amplitudes. So you can see like this, little ripples like this, and then that Fourier transforms into this image over here. So the third dimension here is effectively your brightness. So the amplitude of your pixels. So yeah. But okay, I mean, so in my general opinion, unless you're really well versed in Fourier analysis, it's better to just practically do things and then get a feeling for what's going on. So I spoke a bit about this again last week, just to recap. Basically, you can think of VLBI as making a virtual dish like this, and you're made up of all these little dishes together, basically little mini antennas, and then we remove lots of them, and then we try to reconstruct the missing parts. And the reconstruction of the missing parts is what we call deconvolution, and that is the cleaning that I was just doing in the in diffmap before. And so, yeah, so once again, this is just recapping what we talked about last week. The UV coverage determines the maximum resolution. It's the largest observable scales, and indeed the image fidelity, basically your angular resolution. The shorter spacelines limit the largest angular scales. So basically, interferometers tend to filter out the largest scales. Remember, we talked about this last week. This is called resolving out emission. So that's why you need to have lots of different spacings. You're measuring the Fourier space, if you like. More of these one-dimensional slices, the better you can accurately determine the true structure of the source. And yeah, so this is basically saying all the same things that we said last week. High fidelity is a fancy way of saying that the more of these simple 1D slices we take, the better image we get. I think that's hopefully fairly intuitive. Hopefully you get that. So Fourier fun. So on the left we have a duck, and if we take the Fourier transform of that, we get this this thing over here. It doesn't really look much like a duck, does it? So I mean, actually, if you do know a little bit about Fourier analysis, you'll know how to sort of reconstruct these sorts of things. But nevertheless, and by the way, I got these slides from the University of Western Australia. So the website is down there. I shamelessly copied them, but it's pretty good. And then over here you have a cat, but you can see here, right? So the duck is kind of elongated left to right, and this transfers to a sort of diagonal shaped structure in the Fourier transform. And similarly, the cat here also, it rotates like this, so it's sort of diagonal here and then sort of a little bit less diagonal there. Very hand wavy things to say, but yeah, that's basically it. So that's what the Fourier transform does, and if you get used to it, you sort of get to start to recognize these sorts of patterns in the Fourier transforms as well as the images themselves, of course. And so it's very much related to the idea, that remember the longest baselines correspond to the shortest parts of the image. So it's kind of like an inverse relationship going on. So it takes a bit of practice to get the hang of this. But as I always say, I think the easiest way to learn this is just to do it. Dive in and play with real data. You see here, so we're basically doing what we do in VLBI. We remove Fourier information. So, so on the left, we take rings of information like this, and this affects now our duck. It still looks like a duck, which is good, but we're getting a lot of noise now, right? So we're getting these blue and red smudges everywhere, and basically, it's still basically what we think we're looking at is just looking a bit more ugly. So we have to be a little bit careful. If we didn't know this, would we believe all these swirls around it? Probably not. We'd know pretty intuitively that this is going to be noise, and we try to ignore that. But of course, the more data you remove, the harder it actually becomes to do this. So the amplitudes, basically all they're really telling you is how much power there actually is. So, but the phases tell you where the power is located. So one of the funny things, I really think this demonstrates the power of what's going on. So last week I sort of skipped over this a little bit. I was really only talking about amplitude interferometry actually. But in practice, we actually look at the phases, and the phases are actually really important, and this is where the information really is. So say here the magic source is in the phases. I really can't emphasize that enough. So actually, you can still reconstruct a pretty good image even with bad amplitudes, but if your phases are screwed, you have no hope basically. And you can see here. So on the left, you have basically the amplitude of the duck and the phases of the cat switched, right? So in the top here, you have the phases of the cat, the amplitudes of the duck, and we'll get a cat back, albeit with a bit of noise. And on the bottom, you have the amplitudes of a cat and the phases of the duck. And right here, we Fourier transform it, and we get the duck back. This is really important to know, especially if you want to go more deeply into how this actually works. So the information is in the phases. So if you remember last week, I spoke about the using the timetable analogy of a Fourier transform. So I think I brought it up. It should be here earlier. Here. Here we go. Yeah. So, I said here that, basically, if you have a timetable that is like 7:15, 7:30, 7:45, 8, 8:15, 8:30, 8:45, etc., the Fourier transform of that would be saying that the bus runs 4 times per hour. Right, that's the Fourier transform. The phases of the Fourier transform would be saying that it runs 4 times per hour, but starting at 7:05, and then repeating. So that's what the phases are, because that's telling you where exactly your power is coming from, right? So hopefully that gives a bit of an intuition for wrong thing. What's going on? So you have to be careful with Fourier transforms. So basically, left and right, they are rotated by 45 degrees, but they're completely different Fourier transforms, right? And so this is actually a bit of an artifact of how the Fourier transforms are actually calculated. But basically, it's because the Fourier transform treats the image as a part of an infinite series of identical images. And of course, we can't really deal with infinities in practice. So we have to actually compute something called what's called a fast Fourier transform. So we have to make some simplifying assumptions. And so I won't go into the gory details of this, but you can get subtle effects affecting your image due to the way that the Fourier transform is actually calculated. But I think for now that's getting a little bit too into the weeds of what things we're doing. And noise, so you can see here. So basically, if you've ever done any sort of noise reduction sort of thing using Photoshop even or GIMP or whatever, then almost certainly what's going on is Fourier analysis behind the scenes. Also, by the way, if you've ever used Track ID or Shazam or something like this, almost certainly Shazam is using a Fourier transform behind the scenes. So it's probably Fourier transforming the song it hears and then looking at the peaks in the Fourier transform and matching that. That's actually how Shazam works, or at least I highly suspect so. We've never confirmed it though. Here's a few more examples, so you can sort of see the effects of the Fourier transform. So on the right, you can see we have lots of sharp edges and angles like this in these cubes, and you can. I don't think I really need to describe this to you in great detail. I think it's pretty clear from the images. You know, you have these your left and right bricks here, and up and down bricks are transferring to up and down, but of course rotated around in the Fourier transform, and all these angles are transferring to angles in the Fourier transform. Hopefully that's relatively clear. And you can see, for example, you know, the Z here or the T, they look pretty clear. Even the Q does, but something a bit more complicated like B looks, or even W looks a little bit weird in the Fourier transform. So hopefully that, once again, this is really just me trying to give you more intuition for the Fourier side of things, what we're really doing in practice. And here we go, some more examples. Complicated images, complicated Fourier transforms. And you may notice that there's a lot of power in the center around 0 there. Not a coincidence, it turns out. That's why one of the problems with VLBI is because we generally don't sample that part of the Fourier transform. That's your large scale structures, remember? Yeah, these sorts of things. But there's lots of fine structures in here as well, and that's what VLBI is very good at picking up. And once again, okay, this is another one. So noise. Noise in the Fourier response to lines in the line in the image plane gives noise in the Fourier space. Yes, sorry, that's exactly what I said. I got myself a little bit confused there. And here we go. These are more circular sort of things. So hopefully you're getting an intuition for this. You can look up the details of this a bit more later. And low pass filtering, we can skip past this. So basically, high pass filtering like this is effectively what we're doing in VLBI. We're removing the central component here, and we can detect the outline of things, the bright outline of things. That's effectively what we do in VLBI. So keep in mind when interpreting the images that you make. So you still make out that it's a girl there, but with all these edges left in. Yeah, as I said already, you can think of VLBI as being an edge detector of sorts. UV weighting, I won't deal too much with this. So basically, UV weighting depends on how much you want to weight the longer baseline. So I think that's a little bit outside the scope for today. Probably haven't got time to go into that. And closure phases, this is basically for completeness, but this really is one of the most important things about how VLBI actually operates. So basically, it turns out that if you have 3 or more stations, you can actually solve out your noise effectively due to your problems that you're due to atmosphere or during at your telescope itself. Actually, super powerful technique. So basically, for anyone who's a little bit familiar with this, if you measure your closure phases, if your closure phases are 0, you don't detect anything. But if you do see some closure phases, that means that there is some structure. What the structure might actually be is a little bit hard to say, but we do have some structure there. We can even look at that in the diff map, believe it or not. Okay, now this is a little bit more relevant, I think, for what we're going to be doing now. So this is the clean algorithm. And so basically, as I said before, in VLBI, we are measuring the incomplete Fourier transform of the sky brightness distribution. Basically, what we're trying to do is we're trying to interpolate or even sometimes extrapolate the UV data, the Fourier data that we have. And the most common one that we use is called clean. So basically what's going on, it's an iterative process. You're combining a bunch of delta functions. So delta functions are basically just Gaussians with a 0, just a point, like an infinitesimal point. And they have a flux density but no size. And that's basically what it is. So basically what happens here is Fourier transform your visibility data, and then we find, so it gives us this image data ID. We find the peak pixel, and then we subtract a scale version of the PSF from the peak. So what does that mean? Well, the PSF is the point spread function, right? So if you remember from last week, so if you point at something that is unresolved, you'll get a response from your telescope, and this will be your point spread function. So this is the response of your telescope to something that is unresolved. This is called the PSF. And in the context of VLBI, what we actually look at, what the PSF, we call it the beam, which is, so the beam is this down here, the beam, and that's basically a rough approximation of your PSF, of your point spread function. So basically, this circle is the response of the telescope to a point source, at least in principle. And so what we're basically doing is we're adding lots of these delta functions to the map, trying to make a model, and then we try to subtract a scale version of this model from the PSF. So we're trying to actually improve the PSF, actually. So we want to have a better beam with suppressed. We'll talk a little bit about that in a second. Then we record a delta function at the peak position, and then we convolve these delta functions with the estimate of the central PSF. Once again, like, it's actually not that complicated what it's doing, to be honest. But once again, I think it's easier just to play with the real data, and you can get a feeling for what it's actually doing. So basically, you add more of these delta functions to the map. You subtract it off the beam. You're basically building a model, and then you do this iteratively, and eventually you try to get a good, what we call a clean beam, and then we convolve that with the data, and then we get a clean image, at least in theory. You keep on doing this until things look like basically noise in your residual map. And of course, the residual map is the difference between the model, because the model is what is all these delta functions, and against the data, and this is the residuals, and you want your residuals to look flat, basically. And if that's fine, then you're basically done. The problem with this is that it can be very, very subjective. So you have to be very careful. So let's see, what have I got on the next slide is self-cal. I'll quickly talk about self-cal. I'll just go down here. Has anyone got any questions at this stage? I've covered a lot of stuff here, but is there any questions? In different, I'll bring up map plot. beam. This is the beam, by the way. So this is this is actually the point spread function of this observation. Okay. I suspect that I've just bombarded you with way too much information. But once again, hopefully things will become clearer when you start playing with the real data. So self-cal, that's the other magic source of interferometric imaging. So basically, self-cal works because our system is actually a little bit overdetermined. There are fewer degrees of freedom than there are parameters in the model that we need to reduce. So basically, you make a model using whatever constraints are available. You Fourier transform it to give you the model visibilities. And then if it's a good model, you'd say, also then you fit the data to the model visibilities. It gives you the complex details. Basically, you say, is the model good? If not, you do it again. You make a new model using clean, come back, then you self-cal to Fourier transform it onto the model visibilities, and then you go back and forth like this. So you might have seen that when I was making the image look better, I used clean, self-cal, clean. So that's because I was making a clean model, and then I would self-calibrate it, and then I'd clean it. Okay, so and of course you have to be very careful. Phase self-cal is a lot softer than amplitude self-cal, it turns out, but these are details you don't really need to worry about for now. But yeah, let's go back and look at some. Let's play with the real data again. All right. So I'm going to. There's no picture when you issue matplot. Okay, so what happens when you type matplot? Yeah, exactly. So what actually happens if you type in matplots and then press enter? I think you're a little bit confused. The issue is probably not the file itself, but okay. I think I'm going to have to proceed because I've got that much time. But if you're falling behind, like last week, I can resend the. Just try observe. Something should come up. So yeah, so if you go observe, it then gives you a list of things to there, and then for example here I go 12 like this. Oh, okay, I think that someone's got their mic on. No worries. Yeah, so Octavian, we like if necessary, we can sort this out separately later. I'm happy to spend some time on that if you like. But for now, let's continue. So once again, I reloaded my data. I'm starting from scratch again. So select map size 1024, 0.1. So hopefully everyone has caught up with this now. Okay. So let's go MAPL, just like this. So what you'll see here, this is the residual map. So this is the difference between the model, although there actually isn't a model at this stage, and the data. So it's probably going to look very similar to the point spread function. So if I go MAPL beam like this, this is the point spread function. You can see it looks very, very similar to the, it's called the dirty I-beam. You can see it looks very different, very similar to this. That's your dirty, this is your residuals. This is your beam. Now, the reason you have to be really careful with this, so you have this bright peak in the center. So this is probably real, but you also might notice these things, and these are side lobes. And when you convolve, like when you combine the beam with your visibilities, this can sometimes translate into things in your actual image, and sometimes it's really hard to know if it's due to the noise in your point spread function, the ripples basically in your point spread function, or if it's actually real structure. It can be really tricky to know this for sure. And unfortunately, there's no really perfect way to answer these sorts of questions. It's just the limitations of dealing with data that has so much Fourier information removed. But nevertheless, if in diffmap you right mouse click just to quit the window like this, and you go to MAPL. So this is the residual map. This is the difference between the model and your data. And I say, okay, I think that there is some emission in this region where it's brightest. So this is the region where the difference between the model and the data is maximized. So that's why it looks brighter in this. Cool, you got it. Great. I'm glad to hear that. I'm glad to see that. Cool. Right. So once we put on one box like this, for now we can be conservative. So then we just right click quit diff map, and then we just type clean. So is everybody up to speed? I have a suspicion a lot of people are just watching, and that's fine. So then you type clean. Well, oops, I've got far too many clean components. I'll turn iterers down to 200, something like that. So the number of iterations is about how many times it adds a delta component and then subtracts it from the beam. So now I do that. The residual. So this is the difference between the model and the actual data. So residuals. And you can see now where I put my previous box is now dark. There's nothing there. So now I'm like, okay, but now the bright spot here is over here. And because it's so bright, so hopefully it's not noise. And we just put another box here like this. So I think I believe that. You right click, go clean again. And this time I might say self-cal. So I think that, so look at the data, looks okay. It's a little bit less clear now, but you can see there's lots of noise in the map around here. So yeah, but over here it looks like real data. So you can put a couple more boxes in there like that and go clean. Maybe do clean twice. It's not like this. Okay, let's do a self-cal. It's like this, self-cal. You can see we're actually fitting the data pretty well. Like so. Okay, I'll give everyone a couple of minutes or a couple of moments just to catch up. I'm probably moving a little bit fast there. Yeah, so just /XW. Should do the trick. Try. Like that. Cool, no problems. Good. So then you have the, like this, you're like, okay, cool. Looks like some more emission here. I can go to the clean map. Okay, still looks a little bit ugly. Like so, maybe around here it's real. Do a little bit more cleaning, clean, self-cal, clean. Like so. Okay, and maybe some emission here. Like so. Maybe I can even zoom out a bit. Ooh. If you press Z twice, so that'll zoom out like this. And I can clean a bit. Clean, self-cal, clean. Exactly. So you can see this is interplay between the map with the cleaning and the oops. And maybe there's some emission out here. This is a little bit. This is very faint. So you can see here we're already talking 0.001 Janskis. So it's very faint emission. So maybe it's not even real, but we can play with it anyway. Self-cal. Sometimes you can do it as a loop like this. But now you can see, it's looking very smooth inside here. And that's usually a good sign that you're doing more or less the right thing. So let's have a look. If we go to the MAPLCLN, still not perfect, but it's all right. It's okay. Maybe something there. So hopefully everyone is making the first radio VLBI images, the most high resolution stuff in the world. And so yeah, we're looking at a quasar that was observed not even maybe 18 months ago, something like that. So pretty cool, in my opinion, anyway. Like this. Save it, I would say. Save test.io1 or something. And if you want to do deep, you can go delwin like this. And then you can turn up the emitters to say 1,000. And then you can actually do a deep clean at the end. And this should settle down your noise a little bit. So clean, self-cal, clean. Cool. And then go back to your clean map. There you go. That's looking a little bit less noisy. Still not great, but not bad for 5 minutes of work. You can see here, so you've got this jet that's probably moving at near the speed of light, or probably faster than the speed of light, actually. I was going to talk about that, but we don't need to. I think I found something more fun. And here we go. So, yeah. So there you go. So how are you guys doing in terms of imaging this yourself? Any feedback? Cool. Got one who can follow. Any more feedback or need more time, for example? Like, yeah, this is the point of this, so that I can help you get a feeling for things. So one thing I want to say, especially for people that are just watching, which is, I suspect, most, then let's right-click now. Let's go to the UV plot. So remember this image like this. Now, remember we talked a lot about this last week, about this UV plot. So if I remove all this data here, what do you think is going to happen? Any guesses? Yes, exactly right. You got it. The resolution will be lower, and how will that affect the actual image? No, so actually, this gets into like complex visibility stuff. So if I remove this data, it removes it from the other side as well. But how does it affect the actual image? So if the resolution is lower, which is correct, what will the image actually look like? Because remember, the longest spacings correspond to the highest, the sharpest features of the map. No. Well, let's have a look. Let's save it. Let's have a look at the clean map. There you go. Whoa, it looks a lot blobbier, right? Yeah, it could be a little bit more points. You can see it now, right? So now the resolution is much lower, so it looks a lot more blobby somehow. You're more sensible, at least in effect, taking a look at the larger scales more. You can see the noise itself even looks blobbier. So the source looks actually quite different. But I mean, still broadly speaking the same, still the same direction and stuff like this. But your resolution is lowered. Your source looks a lot blobbier, indeed. So hopefully that gives you a bit of a feeling for what's actually happening here. So by removing the longer baselines, we are lowering the resolution, and this affects the image like this. Cool. Coolies. So then the last step is the most fun one, I think. So this is probably what everyone's been waiting for, at least I hope so. So because we've only got a few minutes left, so oh no, whoops, that wasn't what I wanted to do. Sorry. Wrong button. Oops. Sorry, I wanted to escape the presentation, not it's in the wrong. This is in the same place as just press escape. Here we go. Cool. Great. So go to the horizon.org website like this, like so. And there you go. There's some people that I know in this picture, which is kind of fun. It's Stronghold, Spitler, and Alan. Cool. And then when you're here, go to the For Astronomers tab and click For Astronomers. It's not a good website. Here we go. And then go to who invented this website? This was somebody using a Mac. All right, whatever. I'll just go back to the original page. So this is it anyway. It's in the, I'll put it into the group chat, actually, for the easiest way. Where's the chat gone? Where is it? There we go. Yeah, because you can say I'm not actually the biggest fan of Zoom. Cool. So that's the link there for the Event Horizon Telescope. And then hopefully you can click on that now, and then click the bottom link here, which is the first M87 EHT results calibrated data. And you click the link there. And then you click in the UV factory there. And then you can just take the top one there. Just go copy a link address. Same as before. And then, so I'll quit this now. So I've already done this actually, but I'll do it just a demonstration. Make CDEHT, make directory image, CD image, and wget like this. Cool. So I'll run that through again. So did you manage to get to this page? Now, I guess we're running out of time, so I might just run ahead now, and the motivated people can try themselves. So basically, I'll just run back through the list. So you click on this Cyverse Data Commons DOI here, and it takes you to this data page here. Press on the UV fits, and then right click, copy a link address, and then you just wget the file again, just like we did before. And then that should give you this file here. load up diff map, observe, SR something here. Great. This is not the right file. That's it's wrong. Sorry. Is this one here, not the bottom. What? Hmm. A little bit confused what's going on here. Yeah. Where is it like? Ah, sorry. Yes, it's this one here. This one here, the EHTC first MHM results April 29 fit. So I was telling you the wrong file name because I lost my plot. Try that. Oh, quit again. I'll just go wget. Yeah, so then it should be G on TGZ, I think. Not even sure what. Here we go. Yeah, so then you get this file. It's just basically a file. You just have to decompress it. Then you get this directory here. Because I've only got a few minutes, so I'm going to have to rush through this. So if you want more detail on this, then please contact me. Then go UV fits, and then observe. Also diff map, and then go observe SR71. 09 doesn't really matter which one it is actually. Something like this. Then I go select I. So in this case, we're going to be going a lot more high resolution. So map size now is going to be something like 1024, probably 0.0015, something like this. And I go map plot. W. Ooh. Maybe it's a little bit too much space. Let's make it 5.6. Maybe not. Let's give it 1024. Sorry, 0.15 like this. Let's see how we go. Here we go. That looks look better. So this is, you might recognize this residual map from before. And looks like the brightest thing is maybe here. So clean. Let's go enter equals 10. Clean. Want to be very sensitive here. And already you might be starting to see where my clean windows are going. Let's turn up the indicator to maybe 50, a little bit deeper. Ooh. Okay, that's not working very well. I'm going to start again. So this is sometimes a problem that you get with some of these data sets. Sometimes you put things in the wrong place and doesn't really work out very well. So let's clear mod true. This gets rid of the model. Let's try again. Okay, so that's not right. Let's just leave it here for now. So maybe I need to start again because I self-calibrate. This can be a problem. So if you make something if you self-calibrate your data with the wrong model, then you can break your data, and sometimes you have to start again. This is unfortunately part of the fun of doing this in real life. And map size. Let's go 512 0.015. Oops. Something like this. Something's not right here. You can see 229 gigahertz. That's much higher frequency. What's wrong here? Let me go back to this one. Yeah, so great. Yeah. Okay. So here we go. So yeah, something went a bit disastrously wrong there. I'll work it out. But basically, in this version of the residual plot, you can see that there's a bit of a ring going on here. And if I go to the clean map, you can see here that's your black hole ring. So I've run out of time, so I have to troubleshoot my own imaging there. But that's it. Maybe it looks a little bit more. So this is, of course, not a very in-depth imaging. But if I set map call heat 1,0.5, yeah. That's the black hole image, actually. And you can download the data from the website yourself and try it yourself. So yeah, I know I've covered a lot of detail here. Maybe I'll. So I had to revert back to one of my previously made ones there, so I'm a bit sorry about that. But oops. There you go. So that is that's the image of the ring of the black hole at the center of the M87 galaxy. So obviously this image isn't quite as beautiful as the one that they published. That's in all the press releases, of course. They have more sophisticated ways of doing this, but this is the basics. And if you're interested, I'll happily go into more detail on these sorts of things. So yeah, there you go. Oops. Let me know if you have any questions. Yes, so I'll happily send through all the commands for this.
Thank you, Jeff. So for the participants, if you have any questions, please take advantage of this opportunity and ask Jeff.
And or if you're too shy, you can always just send me an email. I'm always very happy to respond. Yeah, I see some people who are still stuck at the installation stage of diffmap. So yeah. So if you're still interested in trying it out and trying to make your own black hole image, then please contact me directly and we can troubleshoot it. Yeah, no problems.
So thank you again. Let me make a short announcement before we close for today. Next week, the lecture will be delivered on Thursday at 9 a.m. GMT. I will send an email with this, so you'll have this in your email.
Yeah, great. Thanks.
There is a question from Dr. Blagoy. I don't know if this is more addressed to Singh.
I think it's to do with the ALTAS mounts. Well, so I can answer that. So basically, the reason why most radio telescopes are ALTAS is engineering. Basically, it's easier to build a telescope that goes like this than to do equatorial stuff like this. That's the basic answer. Equatorial mounts are harder to build, especially for bigger, heavier things.
And to answer the questions about the video, yes, I have already sent links to the previous lectures, and these two last lectures are to follow, the links for the last two lectures. Okay, so you'll probably have them in a week or two. Sure.
Great, perfect. Then yeah, actually, hopefully I'll even be Cluj sometime in the near future, so I could even do a more in-person, hands-on thing on this, which could be fun if people are interested.
That would be great, yes.
Yeah.
So thanks again, and I think we are done for the week. See you all next week. Thank you. Goodbye.
Yeah. Bye. Ciao.